the recording. What I would like to do today is follow up on some of the latest information on the Chernobyl accident that I haven't had the time to cover last time. So that's what we do right now. And in terms of the classification of the different major accidents that happened in the nuclear field in general. So let me see here how I can get there. And there is a classification that has been set up for the different levels of accidents that happened in the history of nuclear energy generation. And I included it as part of the chapter on the Chernobyl accident. And let's find it here. And I think that's where we stopped. There is some international nuclear and radiological event scale, and it's designated as INES. And it classifies the Chernobyl accident as an event at the level of 7. Later on, we'll study the Fukushima, the Daiichi accident also, and it's also considered as a class 7 accident. But there have been other accidents before in the nuclear field that we should be aware of. In Mihama, Japan in 2004, basically hot water and steam was released from a steam pipe. No radiation was released, but just the release of steam from a hot pipe caused the casualties. 5 people died, unfortunately, in it, and there were 7 injuries. That is the lowest level of accident according to the INES kind of classification. In Tokaimura, Japan, Tokaimura is a facility in Japan that reprocesses nuclear fuel. So they take the nuclear fuel, they dissolve it in acid, in nitric acid, and they recycle it. They extract the plutonium and the uranium, and then they try to use the mixed oxide, an oxide of uranium and the plutonium. So this is a nuclear processing facility. The story goes that the workers in the plant were very hurried to leave the plant for the weekend, and they needed to mix materials, so they used buckets. Imagine a radioactive material moved around in buckets, and they put in more buckets than indicated liquid from the reprocessing plant that contained radioactive fuel, in that case, in the bucket, just being in a hurry. And they broke the safety rules. As a result, you asked the question about criticality accidents. That one was definitely a criticality accident. It was not decay heat in any way, and the criticality unfortunately occurred just for people being in a hurry. That's really sad, and 2 workers died in the process. 40 were injured, received treatment, and survived. But a small accident in terms of a reprocessing plant, that jumps immediately from the level 1, where simply hot steam that can happen in any power plant release can happen, to the level 4. Later on, we'll study the 3 Mile Island in the United States. It's classified as a small break, loss of coolant accident in unit number 2. There were 2 units operating at the 3 Mile Island location. Number 2 was the one that had the accident. We'll study in more detail the human errors as well as the equipment failures and the design flaws, which are the main causes of these accidents. In that case, of course, the core of the reactor did melt. It was damaged. There was a minor radioactivity release. Nobody died in the accident, fortunately. And Unit 1, in fact, continued operation for a long time, but it's just because of aging, it became too old. They have basically discontinued its operation. The 3 Mile Island was a category 5, according to the INES kind of scale that we have defined earlier. Wind scale in Sellafield is a new name for wind scale in 1957 in the UK. Remember, it was a dual purpose plant producing both plutonium and electricity in the UK. We got a fire in the graphite core from the process of releasing the hardness from the Wigner energy, the process of annealing. They did not conduct it carefully. Basically, the graphite caught fire, and then radioactivity from the fuel was released to the environment. The main concern was iodine being released at the temperature of the accent, the graphite burning. And in that case, the iodine end up depositing itself on grazing materials where cows are grazing in the fields. It finds its way to the milk. The milk will find its way to people using cheese or drinking the milk. So in that case, grazing was banned. They kept the cows indoors, and they only fed them on stored hay, alfalfa, or whatever material they're feeding them. And nobody was hurt in a significant way. The reactor ended up being enclosed in concrete. Interesting enough, that's the same situation as happened at Chernobyl. And Chernobyl, interestingly again, has also a core that was had a graphite as a moderator. So both in those cases, the graphite was almost like charcoal caught fire. The site at Sellafield or Windscale was decontaminated, and new reactors, in fact, were built on the site. If you travel to Europe, you'll notice that Europe is a very, very crowded place compared to in the United States. Here in the United States, I would find a new site, but in the UK, they reuse the same site. Windscale is classified as a category 5 accident in terms of severity of the accident on the INES scale. There was an accident that was even more serious than Windscale that happened in the old Union, USSR, which is the Union of Soviet Socialist Republics in 1957. It happened at a place called Chelyabinsk. And that accident at Chelyabinsk was caused by a fault in the cooling system. That was a reprocessing plant, the same as Tokai Mura in Japan. And what they did is that they disposed of the waste into waste tanks. In fact, some people say that it was in a pond outside the plant. The Russians say, no, it was a waste tank. And a chemical explosion happened in the tank. That was not a nuclear explosion, but simply the chemicals exploded. And there was a release of 70 to 80 tons of material from the tank that would have been in liquid phase. They decontaminated the surrounding area, and the place basically continued operating. Notice here when we write tons here, this is the French way of writing ton, and 1 metric ton in French, that would be the SI or Système International System. Try to remember is 1,000 kilograms. If you write only TON, it is identified as the American ton, 2,240 pound. There is a short ton and the long ton also. And last time we dealt with Chernobyl, that happened in 1986. The core became critical. A fire in the graphite core ensued. There was a steam explosion that threw up the lid 800 tons weight up in the air and then back down. And that's what we analyzed in the chapter on the phenomenology of a steam explosion. The fire at Chernobyl burned for 9 days, and basically heroic efforts were done by their firefighters, knowing that they're being exposed to radiation in trying to extinguish the fire. There was also a steam explosion. That was a design flaw in that they placed water in their pressure suppression pool right below the reactor core. And I suspect that the same situation to a lesser degree happened in unit number 3 at Fukushima, but it is not being advertised. It needs to be studied over time. And basically 47 first responders, as they are called, basically lost their lives, unfortunately. And there were 2 casualties in the steam explosion. And there has been, in fact, a significant radioactive release in the area around the Pripyat, in that case, the little town close to Chernobyl. Chernobyl is considered a very serious accident. It's given the highest category, category 7. And when we come to studying Fukushima, it is at the same level as Chernobyl. That one happened more recently, the most recent accident, 2011, 10 years ago. It was classified as a station blackout. So what is a station blackout? A nuclear power station produces its own power to run its instrumentation, its control systems, as well as its safety kind of equipment. And it also depends on the grid in case I do not produce electricity on the site itself. Now, suppose that you lose the power to both the power that you produce at the plant itself, as well as the power that you get from the grid. And we call this a station blackout. In fact, they lost total control of the plant. Their control room turned totally dark because the earthquake did not just affected the plant itself, but it affected a switchyard that was 8 kilometers away from the station itself. And I had some kind of a fun following the power lines to the plant on Google Maps, and you can see that it went eventually to a switchyard where they would get power from the grid. In the United States, plants, all of them have sometimes one connection to the grid or sometimes 2 connections to the grid so that they don't get that classification as a station blackout. The Fukushima accident also is classified as a flooding accident. That did not happen before. So the first time it happened is at the basement where they had batteries and safety equipment were flooded by the water that came in from the tsunami. So it adds to the list of causes of accident in that case, not just the human errors, the equipment failures, the design flaws. It also added the natural disasters as being possible causes of the equation in general. The casualty list has not been on workers at the plant itself. However, unfortunately, 18,000 people lost their lives in Japan from the tsunami itself. There has been definitely hydrogen explosions, and we know that hydrogen in that case is produced from the interaction of very high temperature steam with metals, and hydrogen, if you do not release it from the containment structure, is very highly reactive, and it led, in the case of the Fukushima accident, to hydrogen explosions. 4 units out of 6 units on the site have been decommissioned, even though 2 of the units were not operating at the time where the accident happened. There has been definitely a radioactive release. So the most serious accident then are the Chernobyl that we covered last time, as well as Fukushima at the same level of seriousness, followed by the reprocessing plant at Kishtim in the old USSR. Now it is Chelyabinsk, that's in Russia now. Wind scale and the one at Tokaj Mura and the 3 Mile Island. The interesting thing is that the 3 Mile Island didn't cause any casualties whatsoever, even though the unit 1 in the plant was had a core totally melted. It was totally destroyed in general. This is the situation right now at the Chernobyl plant. They constructed, remember, the plant is at the site of Chernobyl, is north of Kiev, in the north of the present-day Ukraine, and there were 4 units there. The 3 other units continued operation to provide the country and Europe with electricity. There have been talk about shutting them down and replacing them with light water reactors. They probably have been shut by now, but you could see they started building a large silo above the plant that was damaged. This is a chimney that aerates the plant itself. You could see here the other reactor, the other units, reactor 1, 2, 3 there, continued operation for some time. And lately, the concrete silo has been also covered with a steel, large steel containment. The idea here is to allow radioactivity to decrease over time before they can go in and remove it and dispose of it underground. In addition, of course, when you cover it, you do not allow the elements, water and wind, to release the radioactivity to the environment. As I suggested, this is the way it looks like now. The fascinating thing is that the release of radioactivity has been primarily the cesium-137 in the surrounding forests. And we said earlier when we studied the different isotopes features that this is a 20 or 30 years half-life. So the radioactivity has been decreasing very, very substantially. And they have been, in fact, allowing older people to return to their homes. And wildlife, nature basically is restoring the woods around it. They find now wildlife like wolves and wildlife in general, including even deer. So this is the situation there. In that case, the Ukrainians or the Russians basically honor their the people who have been, they call them the responders. You could see here that they were exposed definitely to radioactivity in trying to control the accident. And this is a memorial to those first responders, their firefighters that lost their life in fighting the fire in the plant itself. From that perspective, you'll find that Chernobyl was the most serious accident that happened in the history of the nuclear power generation. A Russian very famous scientist, Valery Alexeyevich Legasov, he was a Soviet inorganic chemist and a member of the Academy of Sciences. He was remembered as the chief of the commission investigating the Chernobyl accident. In 1986, he headed to Vienna, Austria for a conference by the International Atomic Energy Agency. It is located in Vienna, Austria, and they had a 5-hour hearing. He stated that the main cause of the accident were definitely human error. The operator did not really operate the plant as they should have. They should not have overcome the safety systems, as well as the faulty design of having a positive power coefficient of reactivity. I doubt that any type of a plant where you have a different moderator, the graphite, than the coolant, the light water in that design in that case. He is also stressed primarily the human negligence and unpreparedness. And that is a lesson that you have to learn. And sometimes we become complacent in dealing with our own, maybe even safety equipment. And the Winsky moment, as we covered it earlier in the semester, Mr. Winsky suggests that the complacency creates a source of very large risk of source. So when you think that everything is going fine, that is when the probability of occurrence of faulty conditions is the greatest. So he suggests that human negligence and unpreparedness was a bigger factor in what caused the incident. And I quote him here: "Neglect by the scientific management and the designers was everywhere, with no attention being paid to the condition of instruments or of equipment." So we should learn from these lessons. Today, we are living in such a world that we are surrounded by many technologically complex, potentially dangerous systems, both nuclear and non-nuclear. Without those systems, we cannot develop, but nonetheless, they are dangerous. He said also in an interview with NBC News, quote, "That's why it's important to work very hard to ensure that the safety of all technologically complex systems, whether they're nuclear, chemical, biological, should be enhanced. So that is our kind of responsibility as in the engineering profession when we study those accident occurrences. He is also quoted, and he's a very famous scientist, that he commented on the human errors in the violations of the safety rules of the plant. Quote, "It was like airplane pilots experimenting with the engines in flight." And the test, in fact, was conducted by a group of an electrical engineer, headed by an electrical engineer who was worried only about the electrical energy production. So he turned off all the safety features that would tell him that he should not operate his plant at low power levels because of that positive coefficient, power coefficient of reactivity that I tried to describe last time, and the positive feedback control. So we can extend the analogy. It was like a passenger airplane pilot experimenting with the engine of a fighter jet in flight. The most disturbing aspect of the Chernobyl accident has to do with the side effects of the use of complex systems by uninformed individuals. And this is, in fact, an information technology problem that we have to be all aware of. And that is as much as I want to cover about the Chernobyl accident in a thorough way. There was another accident that happened that hasn't been publicized a lot, that tells you more about the design flaws that could happen in the design of a complex system. A nuclear power plant is a complex system in that case. And this is exemplified by the Browns Ferry fire. So Browns Ferry is a plant here in the United States. It's a 3-unit, 1, 2, 3. This is an actual picture of the plant here. 3-unit boiling water reactors. It is near Athens in Alabama on the banks of the Tennessee River. That's where it gets its cooling. It was commissioned in 1966 and finished in 1974. It became the Tennessee Valley Authority's, if you don't know it, the Tennessee Valley Authority is a utility run by the government of the United States. So it's a public utility. The TVA, the Tennessee Valley Authority, runs coal power plants. It runs hydroelectric power plants. It runs nuclear power plants to produce electricity for the complex of the Department of Energy of the United States in the area of Oak Ridge, Tennessee. They also provide power to places like the Alcoa at Knoxville, Tennessee, very close to the Oak Ridge laboratory site. And that is, Alcoa stands for Aluminum Company of America. It produces aluminum. And you know that the production of aluminum needs quite a bit of electricity. In fact, our wind turbines in our area here go as a long power line. The power comes from here around our area, north, south, and east and west, as well as from Iowa, and then goes all the way south to Tennessee. They use also that electricity in the production of aluminum in general. The Tennessee Valley Authority, as I said, is a government utility, the same as the Bonneville utility. That Bonneville is in the area of Oregon, and it also produces power for the Hanford kind of plant laboratory site. The TVA, TVA, by the way, interesting utility. You may like to apply to it, and you can get a government job, the most secure jobs that you can think of in terms of if you get the job, you get promoted and you never get fired. So that's a place to seek a job, at least in the United States, in terms of job security in general. TVA, or the Tennessee Valley Authority, began building a nuclear plant in the 1960s, responding to a growing prosperity in the Tennessee Valley. If you travel to Tennessee, it's basically it's a very beautiful state. It's all green from sources of water and forests. I spent 2 summers at the Oak Ridge National Lab. You may like to spend some time there as a trainee or an intern. And the primary site there is the Oak Ridge National Laboratory. If you go there as a student, you stay at Knoxville. where the University of Tennessee is located. They have 3 power plants, the Browns Ferry plant that we are going to discuss today, Sequoia, and Watts Bar. Watts Bar is a plant where they produce tritium for basically the thermonuclear powers program, and that's why it's run by the government. Those 3 plants provide 30% of the TVA power supply. They have, other than that, coal power plants as well as the hydroelectric power plants. The 6 operating reactors provide about 7,000 megawatts of electricity, serving 3.5 million people in the Tennessee Valley. And 30% of its power supply comes from these 3 plants: Browns Ferry near Athens, Alabama, Sequoia, also in Tennessee, and Watts Bar in Tennessee. So let's study first the Watts Bar nuclear power plant. Watts Bar is a 2-unit nuclear power plant. It's a pressurized water reactor. It is built on the Chickamauga Reservoir. Unit 1 at Watts Bar operated in 1996. And in 2007, basically the TVA board decided to complete the construction of Watts Bar unit number 2. So this is a unit that had been stopped, and they restarted building it again, and they finished it as a matter of fact. So the TVA holds a construction permit for the unit number 2, and they will basically apply for an operating license. They have also, as I said, the Sequoia nuclear plant. That's also a pressurized water reactor that operated about 20 years ago, started operating. There is a whole site where those plants are built. That's a Bellefonte nuclear site near Scottsboro in Alabama. It was selected by New Start. This is a new company started to try to build safe nuclear power plants. And I think we have one of our alumni as the vice president of that company. I think his name is, I forgot, but he took this class, a safety class in general. And basically they are trying to apply for a license to build small nuclear plant units surrounded by a containment structure that would absorb the decay heat without causing a melting of the core. So at some point it might get a license from the NRC, and they will start building small nuclear power plants. The Brown Ferry plants, of course, resides on a very large acreage, about 1,000 acres beside a water reservoir, which would be producing hydroelectric power. The BWRs, in that case, Browns Ferry is not BWR, it's a boiling water reactor. It was the first in the world capable of powering generators that could produce more than 1,000 megawatt of electricity each. So it became the largest nuclear power plant of the world at that time. Yet you'd be astonished how, with all that interest in and technology available, they use something very low technology. In that the accident started with checking for leaks in the pipes that bring into the containment structure from the control room, the wiring that basically measures temperatures and operates the pumps and so on. And so that wiring went through conduits, piping, and that piping used the styrofoam as an insulator. Well, they discovered that there is a leak in the air, just simply stating the situation of the accident. And to check for the leaks, they went on with a little candle. Imagine that, a little candle. And of course, if you have an air leak, the flame on the candle would some kind of wiggle. And they went there checking for air leaks with a candle. Well, lo and behold, the flame from the candle caught up with the styrofoam that you use for packaging, and the styrofoam can catch fire. So the styrofoam caught fire, and they tried to extinguish it by pouring more air into it that spread the fire in the piping, and it became a major accident because now that wires connected the control room to the reactor itself, and in that case, you could lose control on the reactor itself. So in that case, that plant, every power plant, in fact, employs about 800 to 1,000 people with a large payroll. It's a very large enterprise. So let us look at the unit itself. This is a turbine hall, a mother nuclear power plant in everything, except that they used as insulation, first, a flammable material, and second, they go and check for leaks with not say maybe in the construction business that you can go to Menard or any or Lowe's to buy some kind of a smoke generator. You can have a little smoke generator without having a fire to check for leaks in insulation in homes. So they simply were very careless. The design also had this foam insulator that was flammable, and basically it's a 2 billion power plant. The American Society thought that it was a good, well-operated plant. It presented them with a 2007 Utility Achievement Award. So it was a plant running on every kind of criterion as a perfect plant. And it started operating in 1973, and it is licensed to operate for 60, it was licensed to operate 60 years until 2013. The accident was a result of a combination of both human errors and, from the safety perspective, insufficiently designed engineering safety features. So we can say that's basically a design flaw. On March 22nd, 1975, basically a fire started at the unit number 1. Remember, we have 3 units there. The accident resulted largely part of human error. It was near the plant's control room, and 2 electricians were trying to find air leaks in a wall. The hole in the wall was necessary to allow cables through from which the control room to the reactor vessels, and the pipe was sealed with foamed plastic, styrofoam. All right. The electricians were searching for air leaks, and they were plugging the subsequent holes with a foam rubber material. However, the air leaks were not being detected with a scientific device, but rather with a simple candle. Imagine a very expensive power plant that has achievement awards in operation, and they go and use a candle to detect the air leaks. The electricians use the movement of a candle flame in order to locate the escaping air indicative of a leak. The accident began when one of the electricians brought the flame too close to the highly combustible material, which is the foam insulation. Although the permanent seal material was coated with a flame retardant paint, the fire quickly spread from the temporary foam rubber to the entire cable seal. As a result, there was significant damage to the control cables, which compromised many engineer safety features. Now, that's a very interesting, because now you lose control. You lose the contact between the control room and the safety equipment and the control rods and the whole operation of the reactor, and it's threatened to really become a very serious accident. A fire that caused damage to the critical control table would be devastating. From a safety standpoint, there were flaws in using combustible material in a nuclear power plant. You don't do that. The material, a polyurethane foam, amplified the effect of the fire. Once the foam started burning, it would splatter, causing the fire to grow even larger. So that is what happened if you set fire to styrofoam. Attempts at extinguishing the flame with a carbon dioxide extinguisher proved useless. They brought carbon dioxide, and they started trying to cover the extinguish the fire. That's an electrical fire, they said, and you extinguish electrical fires with carbon dioxide. But then they brought in more air by blowing the carbon dioxide into the ducts, so the fire even grew larger. Attempts at extinguishing the flame with the carbon dioxide proved useless. 2 attempts were made by the electricians to extinguish the flames. The first fire extinction blew the lit material through the other side to the wall into the reactor building. So they made it even worse from the outside to the inside, and it started burning rapidly. The second fire extinguisher discharge was sucked through the wall due to the airflow caused by fire, and only caused the flammable material to spread even more. So they are faced now very quickly with the same situation as the people at Windscale faced, a fire in the graphite, but that was not in that case in the graphite. It was a fire in the insulating material. And lo and behold, it's around the control systems. So they lost the connection between the control room and the reactor proper itself. And the analogy is interesting with the Sellafield or the Windscale accident, because initially they would not try to extinguish the fire with water. They tried the carbon dioxide and everything, and it didn't work. And then the fire chief at Windscale in the UK suggested that they have to cool the fire and use water. And when they use water, that is only when they were able to extinguish the fire. Same situation, interestingly enough, happened at the Browns Ferry plant. The initiation of the fire was not only the only event triggered by human error. After efforts made by the electricians to put out the fire whose extinguisher had failed, one engineer attempted to activate an emergency system that would purge the room of oxygen by releasing a large amount of carbon dioxide. There was a chain of events. The first attempt to activate the system was hindered when it was discovered that the electricians had disabled the system that was used to release the carbon dioxide. So they were not able to use the carbon dioxide. The manual turn-on could not easily be activated, either as a result of a construction plate that was hard to remove. So they could not really activate it initially. Once the system was finally activated, the hole in the wall from the now burning cable seal allowed the carbon dioxide to enter the control room. And that caused a great deal of problems for the operators, who began choking. Of course, we cannot breathe carbon dioxide. And that's why in control rooms, in fact, you'll find that they have oxygen masks so that they can breathe in case there is some kind of carbon dioxide. In that case, the operators started choking and putting breathing apparatuses to operate with the carbon dioxide around them. So they really sent the fire into the control room now with the carbon dioxide. Came up the suggestion by the local fire chief, like at Windscale, or maybe he has read about Windscale. Okay, just let's use water to extinguish the fire. The plant operators, after the direction of that superintendent, when everything else failed, for a while continued to combat the fire with the carbon dioxide. It was not suitable for extinguishing the flames. The electrical wires had been heated by the fire, needed to be cooled with water in order to prevent the foam from reigniting. After finally deciding to heeding the advice of the basically the firefighters and using water, if they would have learned about Windscale, they would have used it all the way from the beginning. They used water and the fire was extinguished and the reactor was safely shut down. The damage happened to the control room significantly, and it may have prevented the operation of the emergency core cooling system. And once smoke began to come out from the panel that controlled the engineered safety features, there was, in the control room, you find the panic system, all kinds of lights flashing at you, telling you there is something wrong. And then you have also sounds of alarms, and it becomes a very kind of alarming situation in general. On the Unit 1, cooling pump suddenly stopped working. The reactor operator inserted the control rods and shut down the fission reactor. So in that case, they were left only with the decay heat and not the 1,000 megawatt electrical power generated. Many engineered safety features became disabled. If you don't have control on them with the wiring, you do not have control on the engineered safety fitting, the core isolation cooling, the core spray system that operates for boiling water reactors also stopped operating. The loss of such important safety features and control devices demonstrated the vulnerability of the plant design to single event failures, as they're called. In that case, the fire. Now, the fire happened, it's a single event, but because it affected many of the control systems, the wiring, it became what we called, when we studied fault tree analysis, a common mode failure. So one event of fire caused the failure of many of the other engineered safety features. In other words, a single fire that began in the control room cabling caused a sequence of events that could have led to very catastrophic results. We were lucky it didn't basically progress into a very serious accident. Decay heat, since they were able to insert the control rods, they shut down the main fission reaction, which they should have done immediately from the beginning. They had to deal with the decay heat removal system, and that's why I've been advocating in many articles, for instance, that the nuclear industry should switch from using solid fuels, in which you leave the fission products that generate the decay heat even after you shut down the fission reaction. The alternative is to, of course, use a liquid. So if you move from using solids as a fuel to a liquid, a molten salt as an example, you could basically remove those fission products because you are circulating the liquid continuously, and you eliminate totally the decay heat problem that has been the cause of many of the accidents that basically in the history of nuclear power generation, be it so the 3 Mile Island, the Browns Ferry fire right here that we are reading about today, the Chernobyl accident, as well as Fukushima in general. It took 6 hours after the initial fire has disabled many of the safety systems. The pressure inside the reactor began to rise. The low pressure condensate booster pump could not be able to deliver the cooling water to keep the core covered. So in that case, you could melt the core. This left a single high pressure pump as the only source capable of injecting cooling water, and the single pump would be insufficient at keeping the core covered. A little more than 3 hours later, control of the relief valves was regained and the pressure was lowered enough to allow the high pressure pump. Now, when you have pumps operating in any kind of a pressure environment, when you have a high pressure pump, the high pressure pump can only have a slow discharge. So it can only pump, say, a few cubic meters of water per second. If you operate a pump with a low pressure, then the volume of water that you can circulate by the pump becomes larger. Initially, the plant was pressurized, so they had to wait until they depressurize the system. So in that case, instead of using the high pressure pump with a low flow rate, they were able to use the low pressure pump with a high flow rate. And in that case, they were able to extract the decay heat. So what started with just plugging the cables to the control room ended up becoming a very serious accident that could have caused a meltdown in general. The safety issues, the fire at Browns Ferry highlighted a number of significant risks, flaws, and safety issues that one must be aware when dealing with engineering system. That is engineering system. It's not just nuclear power plants. As you notice here, the most obvious risk illustrated in these accidents is the risk of human errors. Humans are prone to making errors. They don't go and check for air leaks with a flame that can ignite insulator material. In fact, out of town here, I know of a home, a brand new built home by a medical doctor southwest of town, where they went on the construction people went on the roof trying to remove the tiling on the roof, and they used some kind of heating element, and they set the whole house on fire. So this is neglect and human errors to the same level. Adding to the list of human errors, the plant operators battled the fire with carbon dioxide for hours before finally taking the advice of the fire chief to extinguish the flames with water. Nevertheless, it was quick thinking by the reactor operators and understanding of how their plants operates that triumphed over many of the engineered safety features which had been compromised by the fire. The damaged cables presented a single point of failure for a majority of the control and safety system in the plant. And this is a typical common mode failure. One single failure can propagate itself and cause many other components to fail. Despite redundancy in many of the engineered safety features, the single cable tray entering the control room was highly critical to the safe operation of the plant. So there should be more than a control line to the plant. The use of flammable material not near such a sensitive piece of plant infrastructure represents definitely a flaw in the engineering behind the design. As in the case of many industrial accidents, you could see here, this is what we want us to learn from that course, is that it's always the combination of human errors, design flaws, and equipment failures that lead to the most serious accidents in our technological society in general. It is not, say, only a human error. A human error always can be corrected. A design flaw can be overcome, but it's a combination of the three that cause the most serious accidents in general. The Browns Ferry Unit 1 and the rest of the TVA nuclear fleet were shut down in 1985. They restarted some of the units. Unit 1 provides 1,100 megawatts of power, and they have offered the operating sciences licenses and renewed them in May 2006. They last for 20 years. And so this plant is back in operation, and they will have to be rescheduled for another safety review in 2033, 2034, and 2036. So that Browns Ferry accident was recovered from very nicely. But again, the emphasis here is that it's the combination of human errors, equipment failures, and design flaws that cause the most serious of accidents, and you must be aware of that. I'll just ask you to go and reread that chapter and identify the human errors, the equipment failures again, as well as the design flaws in the system. And I think the recording, and wish you all a nice afternoon. Thank you for your attention and coming on such an ugly day out.